Hey guys, and welcome to the latest episode in our Project Gemini multiple stage water rocket project. In this video we're going to talk about our fully 3D printed recovery module for our sustainer stage. This recovery module combines several discrete components into one single module made by using 3D printed parts. The module combines a nose cone, a waterproof camera bay, the avionics bay, and a mechanical parachute deployment mechanism all into one rugged and lightweight package. The basic form of this design arranges the components so that the most efficient use of space is achieved. This reduces weight and also cuts down on the printing time and the plastic used. The avionics bay portion is pretty basic. A compartment centrally located has pockets sized to accept the battery and the altimeter. In this case, the altimeter is a tiny version of our homebrew launchpad altimeter, which we created for another project, which we will unveil in an upcoming video. A 3D printed cover bracket secures and protects the avionics bay and is held in place with nylon screws. In contrast to the avionics bay, the camera bay is much more interesting. A pocket that holds the camera at the ideal angle is built into the recovery module, and the camera slides right in. The nose cone threads into the top of the module and secures the camera in place. Rubber O-rings seal the camera compartment completely, ensuring that water cannot get in and corrupt the video recording, which can happen since our rockets typically land in a lake. The exterior of the recovery module is shaped to avoid impinging into the camera's field of view, and then the recess is painted flat black to prevent reflections or lens flares, similar to a lens hood. To help with the fabrication of multiple recovery modules, we created a 3D printed paint mask that clamps into place, saving a lot of time. The last function of the module is to deploy the parachute, and this is done differently than we have done in the past. Instead of relying on springs or rubber bands to eject the parachute, we designed a completely mechanical deploy system. This system has a compartment that stows the parachute and houses the servo motor, which is triggered by the altimeter when it determines that the parachute should be deployed. The parachute compartment has a door with a lip on the bottom that allows it to hinge out at the top and then free fall. The top of the door is where the magic happens. The upper edge has a protrusion with a slot in it that engages the servo horn and holds the door closed. It was designed such that the door could be snapped closed over the servo horn. Once secured, the door can only be opened by the rotation of the servo, which turns to release the latch and then has a second function where it pushes the door open and prevents it from closing back up. This is how we eliminated the ejection spring, because the door is designed to scoop air when held open by the servo, and this will blow the door and parachute out of the compartment. Here is the first test flight of the recovery module. This was intended to be a normal deploy just to see how it worked. We launched the sustainer alone as a single-stage rocket for this test flight. As you can see, the flight went perfectly and the system worked beautifully. For the second flight, we again flew the sustainer as the only stage, but we set the deploy trigger of the altimeter to a very high descent rate so that the parachute would deploy while the rocket was falling rapidly. This was intended to really stress the system and judge whether it could withstand a high-speed deploy.
3, 2, 1.
The ability to deploy at a high velocity would allow the module to function as an in-flight abort system, which is something that we will need in the future for this project. This flight also went perfectly, even with the very high-speed deploy, and we were very pleased with their performance. That's all we have for this Project Gemini update. We hope that you found this project interesting or perhaps inspired you to do something similar. Let us know in the comments below if you think that 3D printing is the best way to advance water rockets, or if you prefer to make things by hand. It would be very interesting to hear your thoughts on the subject. Be sure to like and share this content if you like this sort of thing, and subscribe if you don't want to miss the next installment in the series. Thanks for watching, and we'll see you next time.
Here goes.